Hello, we are studying today the new chapter Heat and Thermodynamics, and this chapter is started with some basic definitions. We have already studied the mechanics, and in mechanics we require three fundamental quantities. These are the mass, length, and time, and we know the unit of mass is kilogram in SI system, unit of length is meter, and unit of time is second. Here in heat and thermodynamics, which studies the thermal and the heat phenomena, it requires another fundamental quantity that is known as the temperature. And in SI system, the unit of the temperature will be taken as Kelvin. We can define the temperature as the degree of hotness or coldness, and the scales on which we measure the temperature are Celsius scale, Fahrenheit scale, and the Kelvin scale. On Celsius scale, there are the two extreme temperatures, that is the 0 degree Celsius and the 100 degree Celsius. The 0 degree Celsius is the freezing point of the water and 100 degrees Celsius is the boiling point of water. And these two temperatures difference is divided in 100 divisions on Celsius scale. So one division is equivalent to 1 degree Celsius. On the Fahrenheit scale, this 0 degree Celsius is equivalent to 32 degree Fahrenheit and 100 degree Celsius is corresponding. That means boiling point of water is referred as 212 degree Fahrenheit. So there are total 180 difference, and we make the divisions of 1 Fahrenheit. That means 180 divisions. Therefore, the conversion of the Celsius into the Fahrenheit is given by F equal to 32 plus 9 by 5 into value on the Celsius scale. In Kelvin scale, 0 degrees Celsius is referred by 273 Kelvin, that is, it is the freezing point of the water, and 100 degrees Celsius, which is the boiling point of water, is referred as 373 Kelvin on the Kelvin scale. So conversion of the temperature in Celsius to Kelvin is 273 plus degree Celsius. While the heat is a form of energy which is transferred from one body to another due to the temperature difference. And it is important to note that this heat transfer is a non-mechanical process. That means it do not require the mechanical work, or we can say it do not involves the mechanical work. It is the transfer of heat due to the temperature difference. Next, we will define the equation of the state. Equation of the state is a relation between the pressure, temperature, volume, and mass. And this equation of states refers these parameters at the equilibrium state. So we can write V is a function of pressure, temperature, and the mass. So we can say state of the matter of any material, that is having the mass m, is described by its pressure, volume, and temperature. And in general, these cannot vary independently. That means there is some relation, and that relation is given by V equal to function of P, T, and M. M is the mass of the matter, and this relationship is called the equation of state, and this state refers the equilibrium state. Next term is the ideal gas, which we have already discussed in the gases. The ideal gas is defined by the equation. This is the PV equal to nRT. This equation is valid for the ideal gas. The gas which have zero volume or negligible volume, that means gas molecules have negligible volume, and the attraction between these molecules is also negligible, then we can say that gas is the ideal gas. And the behavior of the real gas, if we check the gas which is real at low pressure and high temperature, that real gas is very close to the ideal gas. So we can say a gas at low pressure and high temperature is very close to the ideal gas. That means we can treat that gas as a ideal gas. So we have to remember this equation. This is the ideal gas equation, PV equal to nRT, and here the interaction between the gas molecules is negligible or zero, and also the volume occupied by the gas molecule is zero. And here P is the pressure V is the volume, R is the ideal gas constant. This R is the universal gas constant. That means it is same for all the gases and its value is 8.314 joule per mole per Kelvin. And if we convert this joule into the calorie, then it will comes to the 1.99 calorie per mole per Kelvin. As we know, 1 calorie is approximately equal to 4.18 joule. So this is the using this conversion we can calculate that 8.314 joule per mole per Kelvin is equal to 1.99 calorie per mole per Kelvin. For fixed mass of the ideal gas, if mass is fixed, we can say this mass is a constant or fixed. In that case, the gas is having molecular weight, say capital M. This is the molecular weight. So if mass is fixed, then we can say number of the mole of the gas is also fixed because number of moles are equal to the mass divided by the molecular mass. Molecular mass is already a constant term and mass is given fixed. So we can say the number of the moles is also fixed. So for an ideal gas which have fixed mass, or we can say the fixed number of moles, that means the ideal gas PV equal to nRT can be written as, because R is already constant and N is taken constant for a fixed mass, this implies that PV by T equal to NR equal to constant. So for fixed mass NR is constant, so we can write PV by T equal to constant. This implies that for the gas at different pressure, volume and temperature, the relation will be P1 V1 by T1 will equal to P2 V2 by T2 for the same gas. In this equation, if T is also constant, then PV will be constant. Product of the pressure and of volume will be constant. And this is a Boyle's law, which we have already read. And this is not a fundamental law like the Newton's law or the law of the conservation of energy.